In this Learn Electrics video, we will look at how we can make cable size calculations, how we can choose the correct breaker or fuse sizes, and how we can determine if the voltage drop in the cable is within limits just by using the wiring regulations book, nothing else. We will look at both single-phase and three-phase applications. All references to page numbers and tables will be to BS7671 Wiring Regulations 18th edition Amendment 2, the Brown Book. The Amendment 3 supplement is available as a free download, and there is a link in the description to this video. Paste this into your browser, download and print the supplement, then attach it to your existing Brown Book, and this will make your Amendment 2 book compliant with Amendment 3. In this video, we will look at and explain a number of important items related to cable size selection, such as the relationship between IB, IN and IT, C factors, reference methods and voltage drop, and power, volts and amps, both single phase and three phase. This video will be especially useful for understanding and using the BS7671 book in preparation for exams and just improving knowledge. Also for Level 3 assessments for apprentices and technical diploma students, and for written exams and those involved in circuit design. We should begin with single-phase circuits and work through a typical example. Let's look at the type of question you might have. A single-phase 230 volt AC circuit is to be installed to supply a 6 kilowatt water heater that is wired in 70 degrees Celsius thermoplastic insulated and sheathed flat cable with a protective conductor, what most of us will call twin and earth cable. The copper cable will be clipped direct throughout its length of 25 meters. The ambient air temperature is 35 degrees Celsius and the cable will pass through a thermally insulating wall of 100 millimeters thickness. The circuit is to be protected by a Type B BS 60898 circuit breaker of a suitable rating chosen by you. And then I've included 6 prompts, 6 things that we should answer, and we will work through each one. Number 1, calculate IB. 2, select a suitable circuit breaker for IN. 3, calculate IT. And then 4, select a suitable cross-sectional area conductor for IT. Finally, calculate the actual voltage drop. And then 6, confirm that IB, IN, IT and voltage drop are correct. A drawing of the circuit can help, and I will often sketch what the question is telling me. It doesn't need to be a work of art. A simple sketch that you can understand yourself is enough to help. It also helps to make a quick list of what information the question contains, as shown here. The action of writing it down, combined with a drawing, really helps you to understand the question and avoids confusion. You can also make notes of where to look, extra information, etc., and all this saves time and improves accuracy. And a list of what we need to know can help too. It will help to identify what you know and what else you need to know. I've included the formulas here, the tables and page numbers that we need, and now we can start to find some answers. A quick reminder of the question, and then let's get into it. This is an important formula, and we must satisfy this. Look at the direction of the arrows. IB must be equal to or less than IN, and IN must be equal to or less than IT. IB is the design current, the load that the manufacturer of the equipment or the designer of the circuit has designed it to operate at. IN is the nominal current rating of the protective device, what it says on the front of the breaker. A 25 amp MCB has a nominal rating of 25 amps, and IT is the tabulated current carrying capacity for the type of cable and installation methods. We must ensure that the cable is always the strongest part of the circuit electrically. Step 1 is to calculate IB, the design current, a very simple power law calculation. IB, the design current, equals power divided by voltage. We have 6000 watts divided by the nominal voltage of 230 volts and an answer of 26.1 amps. So IB is 26.1 amps. For step 2, we can select a suitable protective device for IN. IN is the nominal rating of the protective device, and the question directs us to choose a type B BS7671 MCB from the standard ratings supplied in the tables. We use table 41.3 on page 68 to find a type B breaker that has a rating equal to or greater than 26.1 amps. This is 32 amps, as shown in the red boxes. And now we have IN at 32 amps. At step 3, we calculate a minimum value for IT. IT must be equal to or greater than IN divided by the C factors. C factors will derate a conductor's current carrying capacity. It will reduce the maximum current that can pass before the cable reaches its limiting temperature, in this case 70 degrees Celsius. We are interested in CA, the factor for ambient air temperature found in table 4B1 on page 441, and CI, the thermal insulation factor, is found in section 2.6 on page 423. Looking at these two pages, we can easily see that CA is a derating factor of 0.94 and CI derates by 0.78. Now we can make a calculation. We have IN as a 32 amp breaker, CA as 0.94 and CI as 0.78. So IT must be equal to or greater than 32 divided by 0.94 and 0.78 multiplied together. We have 32 divided by 0.7332, and this calculates to 43.65 amps. IT, the tabulated current carrying capacity of the cable, must be at least 43.65 amps. Now we can find a suitable cable size by comparing the IT value to table 4D5 on page 456. Step 4 is selecting a cable size, and this is table 4D5, which is specific to twin and earth cable. Look down the column for clipped direct and find an amps rating equal to or greater than 43.65 amps. This is 47 amps. Now traverse left along the row to find the cable size, which is 6 square millimeters. So for 6 square millimeter copper conductor, IT is 47 amps. You must understand that although we have an IT of 47 amps, the actual load IB will remain at 26.1 amps. The load will not change. What has changed is the conditions affecting the cable, and we must choose a cable size that can tolerate these conditions, that will not overheat. Step 5 is calculating the actual voltage drop in the cables. There is a maximum permitted voltage drop, and this is stated in table 4AB on page 430. We should be looking at a public low voltage distribution system, the national grid, and other uses, in other words non-lighting circuits, which is 5% of the nominal voltage. The question tells us that the voltage is 230 volts, and we should know that a water heater will be other uses. Calculating 230 volts multiplied by 5%, or 230 volts multiplied by 0.05, will give us 11.5 volts. The maximum permitted voltage drop for this circuit is therefore 11.5 volts. Now we know the maximum permitted, let's calculate what the actual voltage drop will be. The formula is shown in the blue box. We know IB from a previous calculation, and the length is given in the question. and dividing the top row by 1000 will convert the answer from millivolts into volts. We now need to find the millivolts per amp per meter number for 6 square millimeter cable. This is the number of millivolts lost in the cable for every amp that flows through every meter of cable. Find table 4D5 on page 456 and look at the leftmost column, the conductor size. Find 6 square millimeters and travel horizontally to the rightmost column where we find the number 7.3. Now we are ready for the calculation. We can enter the known values into the calculation and we have 7.3 multiplied by 26.1 multiplied by 25 and all divided by 1000, and out comes the answer 4.76. The calculated actual voltage drop is 4.76 volts. Step 6 will confirm that IB, IN and IT and the voltage drop are all correct. A simple check. Here 26.1 is less than 32, is less than 47, all good. And the actual voltage drop is 4.76 volts, which is less than 11.5 volts, also a good result. To answer the question, 6 square millimeter cable is chosen, IB is 26.1 amps, IN is 32 amps, and IT is 47 amps. The actual voltage drop is 4.76 volts. Checking, we find that IB, IN, IT and the voltage drop are all correct. Now we can look at three-phase cable selection, and it really is very easy. Three-phase cable calculation follows the same method as single-phase, except IB has an extra calculation. Different tables will be used for conductor sizes, and the maximum permitted voltage drop is likely to be different. Again, let's have a question to demonstrate this. A new supply to a three-phase 9 kW 400 volt AC pump unit is to be installed using 70 degrees Celsius thermoplastic multi-core armoured cable, or as we call it, SWA, and clipped direct throughout its length. The circuit is 55 meters in length and the cable will pass through a 200 mm thick thermally insulating wall. The ambient temperature is 40 degrees Celsius and a suitable Type C BS7671 circuit breaker is to be selected. Again, the same 6 steps to find the answers. Make a list of what we know from the question. Step 1. Begin with calculating IB, the design current. This time, for three-phase, the power is divided by the square root of 3 multiplied by the nominal volts. We have 9000 amps on the top divided by 1.732 and 400 volts multiplied together. This makes IB equal to 12.99 amps, which we can round up to 13 amps. For step 2, find IN in the appropriate table. This will be table 41.3 on page 68. Find Type C breakers and find a value equal to or greater than 13 amps, which is 16 amps. So IN, the rating of the MCB, is 16 amps. Step 3 is calculating IT, and the first thing we must do is to find the values of the C factors, CA and CI. CA will be found in table 4B1 on page 441 with a D rating value of 0.87, and CI is in section 2.6 on page 423, showing a D rating factor of 0.63. Putting these numbers into a calculator, 16 divided by 0.87 and 0.63 multiplied together gives us 16 divided by 0.5481, which equals 29.19 amps. So IT must be equal to or greater than 29.19 amps. Now find the cable size that will take this current. Step 4. Selecting a cable size. This is armoured cable, SWA, so we use table 4D4A on page 454 for this question. We need a cable that will take at least 29.19 amps reference method C or clipped direct and 3-phase AC. This is 33 amps and a conductor size of 4 square millimeters, so IT is 33 amps. What have we got so far? We now have IB equal to 13 amps, IN is 16 amps and IT is 33 amps for a cable CSA of 4 square millimeters. Now we can calculate the voltage drop in the cable. Step 5. Limits for maximum permitted voltage drop are shown in table 4AB on page 430. This is a 400 volt circuit, so the maximum is 5% of 400 volts, which is 20 volts. Now calculate the actual voltage drop for the cable. Go to table 4D 4B for armoured cable on page 455. We need the MVAM number for a 3-phase AC circuit and 4 square millimeter cable. This is 9.5. We now have all the data that we need to calculate the voltage drop. Put the numbers into a calculator and our answer is 6.79 volts. For step 6, let's check that everything is correct and within limits. 13 is less than 16 is less than 33, so that is okay. And 6.79 volts, the actual voltage drop, is less than the maximum permitted of 20 volts. All okay. So answering the question, 4 square millimeter SWA cable is chosen. IB is 13 amps, IN is 16 amps, and IT is 33 amps. The actual voltage drop is 6.79 volts. We can say that IB, IN, IT and the voltage drop are all correct. 3 test questions to try yourself. Take your time with them and understand each step. Pause the video on each slide and attempt an answer. The answers to each question will be on the slide following each question. This is question number 1. Read the question carefully, make notes as required, and work through each of the 6 steps shown below the question. Follow the steps in order shown, and the answers are on the next slide. Pause the video and find the answers. These are the answers that you should have. Don't worry about small differences in decimal points. It all depends on how you round up or round down. I have 21.74 amps for IB. You might have 21.75 or 21.73, and both are perfectly okay. If, however, you have a big difference, go back over your calculations and find where you went wrong. This is good learning practice and will teach you a lot. Now move on to question 2, which is a 3-phase circuit. Again, read the question carefully and make notes. Follow each of the 6 steps to arrive at the solutions. Pause the video now. Answers to question 2 are on the next slide. Shown here are the answers to each of the 6 steps for question 2. Pause the video and check your answers. And finally, question 3. Be careful with this one. It's single phase in armoured cable and is a very long circuit, so watch the voltage drop. Pause the video and find the answers. Here are the answers for question 3. With a required IT of just over 11 amps, the table directs us to 1.5 square millimeter cable, but with an 80 meter circuit length, the voltage drop is too high. This is single phase, so the maximum is 11.5 volts, and we have calculated 18.17 volts. Clearly, this is not a correct circuit, but what can we do? Recalculate the voltage drop using a larger CSA. Let's try 2.5 square millimeter armoured cable. Find the MVAM number for 2.5 square millimeter cable and find a new answer. Here are the new answers for question 3 in blue. Using 2.5 square millimeter cable, we now have an actual volts drop of 11.275 volts, which is just below the maximum of 11.5 volts for a 230 volt circuit. Increasing the cable cross-sectional area will decrease the voltage drop. More copper makes it easier for the current to flow and less volts are lost in the cable. Here's a summary of the formulas to use and the 6 steps that were used in the test questions. It may be useful to make a note of these and practice with them until they become second nature, especially if you have exams or written assessments in the near future. Thank you for watching. It really is appreciated, and I hope that you found this video helpful in your studies. Please subscribe to our channel to get access to all of our videos, and remember to click on notify to be sure of not missing our next video. And don't forget, you can also type in Learn Electrics into the YouTube search bar to go directly to our channel at any time from any computer or smart device. We are constantly adding new videos to our channel, so don't miss the next one. And once again, thank you for watching, and we hope to see you again very soon.